Good day to everyone. So in this video, we are going to discuss about the finding the viscosity of the high viscous liquid, so which is called the Searle's viscometer. So this Searle's viscometer is actually used to find the viscosity of the high viscous fluids like castor oil and glycerin, etc. So this Searle's viscometer is also known as the rotation viscometer. So the schematic diagram of this apparatus actually look like this. In this, we have a two coaxial cylinder which is having the different radius. So one is the outer one and another one is the inner one. So the space between these two coaxial cylinders actually the space between the two coaxial cylinders is actually filled with the fluid, which we have to find. Whose coefficient of viscosity is, can be determined. Let us consider this inner cylinder is taken as A and the outer cylinder is taken as B, and this outer cylinder is actually fitted with the rotatory motor. You can fix the rotatory motor here, so that suppose if you are rotating the motor, this outer cylinder can be rotated with the angular velocity of capital omega about the common axis. So that once this outer cylinder is rotated, what happens is this the fluid which is actually filled in this gap is also trying to rotate, so that the fluid which is in contact with the outer cylinder is actually also rotating with the same angular velocity omega. And once if you are moving away from this outer cylinder and if you are moving towards the inner cylinder, then the velocity is actually, the angular velocity is slowly decreasing. And due to this rotation of this fluids inside this in between the two liquids, the torque will be naturally be communicated to the inner cylinder also through this fluid, and its magnitude, the magnitude of the torque is actually depending upon the viscosity of the fluid which we have filled with this in between the cylinders. Suppose if you consider the small slice of the cylinder, which will look like this figure is shown in here. So this is the outer cylinder, and this one is inner cylinder, which is having the radius of the inner cylinder is having the radius of A, and the outer cylinder is having the radius of B. So the cylinder is actually mentioned as A and B, which is actually rotating with the angular velocity of omega. So the angular velocity of the cylinder is actually limited to the flow of limited to some limit. So that the liquid between these two cylinders is actually having the laminar flow. So the outer cylinder is actually rotating with respect to the inner cylinder with angular velocity of omega. Therefore, the layers of the fluid in contact with the outer cylinder is actually rotating with it with its own velocity of the same angular velocity capital omega, and the velocity of the other layers progressively decreasing as we move inward toward the inner cylinder. So the angular velocity is actually slowly decreasing once you are moving from outer cylinder to inner cylinder. So that if you consider the liquid layer which is very near to this outer cylinder is actually will be equal to 0. Therefore, there is a relative motion between the different layers of the fluid due to this the variation in the velocity. Suppose if you consider the coaxial cylindrical layer C, which is of the fluid at the distance from R from this origin O and the thickness of dr. So if it is rotating with an angular velocity of omega, then I can equate the linear velocity and the angular velocity. Suppose if you consider the linear velocity as taken as b and omega is the angular velocity, so I can just equate this angular velocity and linear velocity with the relation v is equal to r times of omega. So r is the radius of the cylindrical layer which is from the origin. And if we consider the length of this cylinder is taken as L, or the height of this liquid, the filled liquid is actually taken as L, then the viscous force F can be acting on it can be calculated according to the Newton's law of viscosity, which we already derived at F is equal to um, eta times of A into dV by dr. So this is we have already derived that the force is actually directly proportional to the area into dV by dr. So we have added the proportionality constant, which is the coefficient of the viscosity, so that I can write the force which is acting on this taken as the F is equal to eta into A dV by dr. So the dV by dr is the velocity gradient or the rate of change of velocity with respect to the r, with the radius r. So now I can write this dV by dr from this relation V is equal to r omega. So I can just substitute the values of V in this equation so that I can write as d by dr of V omega. And if you try to differentiate this, we get the V into d omega by dr plus omega into dr by dr. So the dr will get cancelled. So the dV by dr will be equal to omega plus V d omega divided by dr. So this is by the velocity gradient dV by dr, which is equal to omega plus V d omega by dr. And since this omega is a constant quantity and would represent the velocity of the layer in the absence of any viscous medium, that is, if it were the rotate like a rigid body, it does not contribute to all towards the velocity gradient, so that we can just neglect the constant angular velocity omega, so that I can write dV by dr, which is equal to V times of d omega by dr. So this is the velocity gradient. Sorry, this is actually r. I can just represent just differentiating V and r like this. So dV by dr is equal to r times of d omega divided by dr. That is my velocity gradient, which is responsible for the viscous drag on the imaginary cylinder, which we have considered here. The layer which is considered here. Hence, this viscous drag or force F is equal to, which can be written as just substituting this dV by dr into this equation. I can write it. I can write the F as that is a drag force F, which is equal to eta A r times of d omega divided by dr. And you can see this eta is the coefficient of viscosity and A is the area. Suppose if you find out the area of this cylindrical wire, I can write it as this is equal to eta times of 2 pi r times of L into r d omega divided by dr. Here the 2 pi r into L is the area of the circular layer which we have considered, so that I can write it as F is equal to eta times of 2 pi r squared L into d omega divided by dr. So that is the drag force which is acting on the solid liquid due to this the rotational motion. And following this, I can easily find out the moment of the force or the torque T can be written as F into R, so that I can which is the moment of force which is equal to force into the radius R, so that I can just substitute this the force, the value of F is here in this equation. So the torque which will be equal to eta 2 pi R, and this R will be multiplied with the R cube L into d omega divided by dr. Or I can rearrange this equation as 2 pi L into eta d omega divided by t, which is equal to dr divided by r cube. So I just taken all the r parts into the one side and the remaining parts as the other side, so that the effect of the whole fluid in between the cylinders A and B is obtained by just integrating this expression with the limits of omega which is equal to from 0 to omega is equal to omega is 0 inside the inner cylinder, and the angular velocity can be just outside near the outer cylinder is taken as a capital omega, and for the limit for the r is actually from A to B. So the r is varying from A to B. So using this two limits, I can integrate this equation. So I can write this equation as, so integration of 0 to omega 2 pi L eta d omega divided by t. This is equal to integration of from a to, sorry, b to a dr divided by r cube. So I can take the constants outside, only the d omega is the we are going to integrate, so I can just take the other values outside, 2 pi L eta divided by t, and if you integrate this equation, you get the omega, and if you substitute the value of omega, you will get HVC is equal to omega, and the other limit is 0, which is equal to dr by r cube can be written. If you are integrating this equation, you will get the 1 by 2 r squared. So that suppose if you are substituting these values of a and b, I will get 1 by 2 times of 1 by a squared minus 1 by b squared. Or I can rearrange this equation to find out the torque value T, which is equal to the 2 will go on this side, so that 4 pi L times of eta omega divided by 1 by a squared minus 1 divided by b squared. And if you take the LCM of this 1 by a squared minus 1 by b squared, I can write this as 4 pi L eta omega a squared into b squared the whole divided by b squared minus a squared, which is the expression for the torque which we have found, okay, which is taken as equation 1. So this torque is actually tends to accelerate the motion of the fluid in between the layers C and A, but this fluid being in a state of stationary motion, and the inner cylinder A must be also be exerting the equal retarding torque, that means opposite torque on the fluid in contact with it. And since the action and reaction are equal and opposite direction, it follows that the equal and opposite torque T is also exerted on the inner cylinder A, tending to rotate it through the angle of some angle theta due to this the torque motion, until it is actually just balanced the restoring torsional torque T. And this restoring torque is actually given by this the suspension wire, which is actually suspended by the small cylinder, so that if I consider the C is the torsional couple, which is actually set up to in the suspension wire per unit twist, is a couple per unit twist, and then we have we can just relate this torque on this torsional couple as T is equal to C times of theta, where theta is the deviation of the rotation of the angle of rotation of this small cylinder small cylinder, so that I can just substitute the values of T, and I just equate this C theta with this equation 1. So I find that C theta is equal to 4 pi L eta omega a squared b squared whole divided by b squared minus a squared. And from this I can easily find out the coefficient of viscosity. So I can just rearranging this equation eta, which is equal to C times of b squared minus a squared into theta divided by 4 pi L eta omega a squared into b squared. So this is the expression which is used to find out the coefficient of viscosity of the corresponding liquid. Okay, so in this case which we have discussed here, we have not taken into the account of the torque of the inner cylinder, because this torque on the base of the inner cylinder not only depends upon the radius of the cylinders A and B, but also depends upon the distance between the two bases of the two different cylinders. Suppose if I consider the torque of the cylinders, the inner cylinder is taken as TB, torque of the inner cylinder is taken as TB, then I can just write the same expression as suppose by taken as T1, which is equal to C theta, that is equal to C times of, so this torque T1 is the combination of both the inner cylinder as well as outer cylinder, so that I can just add this TB into this expression, so that I can write this expression as 4 pi L eta omega A squared B squared divided by B squared minus A squared plus TB. So this may be taken as equation 3. However, suppose if you are doing the actual experiments, we are actually trying to eliminate this TB altogether just by repeating the experiment with the different length of the length of the length or height of this liquid or a cylinder of the A and B, so that if now the total torque of suppose if we to consider the another torque T2, which is equal to C theta, that means you are going to replace the inner cylinder with another cylinder with the length of taken as L prime or L prime, and then you can again doing the same experiment, and you are going to find out the torque T2, which is equal to C theta prime. That means the theta prime is the angle of rotation of this inner cylinder, so that I can just writing the same expression for 4 pi L prime eta omega A squared B squared divided by B squared minus A squared plus TB again, so that here this theta prime is the angle of rotation of the inner cylinder, which is having the length of L prime. So this equation is taken as 4. Suppose if I try to subtracting this 3 and 4, I can get C theta minus C theta prime, which is equal to, I can just take all the constants, 3 minus 4, so that I can just take all the constant outside, and this TB and this TB will get cancelled, so that I can write 4 pi eta omega A squared B squared divided by B squared minus A squared into L minus L prime. Or I can just take the C as outside, so that I can get T theta minus theta prime, which is equal to 4 pi eta omega A squared B squared divided by B squared minus A squared L minus L prime. And from this I can easily find out the expression for this coefficient of viscosity eta, which is equal to C times of B squared minus A squared and theta minus theta prime, the whole divided by 4 pi eta omega A squared B squared into L minus L prime. So now this is the expression for finding out the viscosity of the dense fluid when we are considering the torque of the inner cylinders also. Okay. So using this expression, suppose if the other values, all the values which we have seen here, is everything is a constant. The B, A, B are the radius of the inner and outer radius, theta and theta prime, which we can calculate from the experiment. As similarly, C we can also calculate from this experiment, and the omega we can actually have in the rotational motor, so that we can set up the rotational motor with some different angular velocity, so I can fix this omega also. Then the L and L prime was the difference between the two different cylinders which we have considered. So only the parameter C, the value of C, which should be calculated using the you have to calculate the value of C using the experiment, so that I can find out the coefficient of viscosity. So the essential parts of the apparatus used for the experiment is shown in this figure, where the outer cylinder is actually B is actually clamped with the table T, which is actually also having which is actually attached with the belt to the motor, so that you can just rotate the outer cylinder. Then the inner cylinder A is actually suspended inside the B by means of the long thin suspension wire, which carries a small mirror in it, so that which can be enable us to find out the angle of rotation theta caused by the constant rotation of this outer cylinder B, which can be noted accurately by using the scale and telescope arrangement. So the value of C, that means the torsional couple per unit twist of the suspension wire, is determined by first setting the inner cylinder, only just taking the inner cylinder into the torsional vibrations about it, and then it is that means you are going to do this experiment first with the inner cylinder alone, and then after completing the then you can just calculate the what is the value of theta and the rotational everything you have calculated. Then after that you are going to add the a small hollow metallic disc on, which is actually situated kept on the above the this inner cylinder, and the moment of inertia of the inner cylinder is taken as I prime, which is already known from the experiment. And then again you are going to find out the what is the time periods of this rotation, and the time periods of the rotation is taken as T1 and T2. Suppose the T1 is the time period of the rotation only for the hollows, only for this inner cylinder, and T2 is the time period which you have calculated just by keeping the disc hollow disc on the cylinder. Then you have calculated that T2, so that I can find out the time period T1, which is equal to 2 pi times square root of I divided by C, which we have already calculated. This expression is already we know, and then you can easily calculate the T2, which is equal to 2 pi times root of I plus I prime divided by C. So here I is the moment of inertia of the inner cylinder, and I prime is the moment of inertia of the hollow sphere, which hollow cylinder, hollow disc, which we have kept in above this small inner cylinder, so that I can just find out this T1 and T2. So I can write this expressions T1 squared, which is equal to 4 pi squared of I divided by C. Similarly, this one is T2 squared, which is equal to 4 pi squared I plus I prime divided by C. And if you try to subtract these two expressions, so that I can just T2 squared minus T1 squared, which is equal to 4 pi squared I plus I prime minus I the whole divided by C. So this I and minus I will get cancelled, so that T2 squared minus T1 squared, which is equal to 4 pi squared I prime divided by C. So from this equation I can easily calculate the torsional couple per unit twist, which can be written as C is equal to 4 pi squared I prime divided by T2 squared minus T1 squared. So this is my value of the C, which can be substituted into this equation, so that I can find the final answer as, so I can write this eta here, eta which is equal to C times of B squared minus A squared times theta minus theta prime divided by of the whole divided by 4 pi omega A squared B squared into L minus L prime, and the C value is here, so that I can just substitute the C value here. What I get is theta is equal to 4 pi squared I prime B squared minus A squared theta minus theta prime divided by this 4 pi omega A squared B squared L minus L prime. So the T2 squared minus T1 squared, so that this 4 and pi will get cancelled. So finally the expression of eta can be written as I prime B squared minus A squared theta minus theta prime the whole divided by omega A squared B squared L minus L prime and T2 squared minus T1 squared. So this is the expression for to find out the coefficient of viscosity, and I prime is actually which is the moment of inertia of the known disk. So all the other values we can calculate from the experiment, and then you can find out the coefficient of viscosity eta. Okay, so one important thing you have to do this experiment is that the speed of the rotation of the outer cylinder must be kept low, some very small value. Otherwise, suppose if the rotation is very high, then the fluid flow become a turbulent flow, not a laminar flow, so that the T is no longer proportional to the the angular velocity omega. So this may be clearly avoided by just rotating the outer cylinder with some lower speed, lower angular velocities. So one more thing is this same experiment can be used for the liquids as well as gases. So for the liquid, what we have to do is sometimes the length of the liquid filled with this outer chamber is actually vary with different lengths L and L prime. And suppose if you are using the gas inside this chamber, then we can change the length of this inner cylinder for L and L prime. So either way, you can calculate the viscosity of the high dense liquid as well as the air, and the expression will be expression which we have calculated here is same for the both air as well as the liquid. So that only this L is actually depend. I mean the vary. Suppose the L and L prime is, suppose we are using the liquid, this L and L prime is the height of the liquid which you have filled, and suppose if you are using the gases, then the length of the cylinder, inner cylinder will vary with the two different lengths L and L prime. Okay. Okay, stop here. Suppose if you have any doubts, then we can discuss it in the online class. Thank you.